Okay, algebras, what I want to model for you is an example of annotated reading. There are no problems for you to solve on this entire page. But instead what we're going to be looking for is making sure that we are reading with purpose. And we want to go through and talk about each of these ideas as a review and as they relate to the picture. So when we talk about our domain and range, make sure you understand, and if you want to, get some colored pens to really think about what domain and range represent. This domain is our input values. So when we talk about domain, we're talking about everything that we can put into a function. So when we're looking at our graph specifically, we have an interesting combination here because my domain starts here at this x value of -5, but then this arrow tells me that it continues on in both directions forever, or in that direction forever. When I'm looking at my range is my output values, and my range is going to be what possible values are coming out of x. So when I look at this graph here, the maximum that my graph is at 5. So when I'm using interval notation to talk about domain and range, your domain, you always go from least all the way up to greatest, reading from left to right. So the smallest my domain value here is -5, and the largest input value I could possibly have is infinity. My range, remember I start at my least, so the smallest that my graph can possibly be is a -infinity. And what is the very maximum value of my graph? In this case, it's going to be +5. Remember, with interval notation, there's a difference between including the value and not including the value. You always want to use your parentheses when you're dealing with infinity. And you always list from small to large. It's a shortcut, so we need to know how to read it. All right, let's talk about these next notes. When we talk about our intercepts, our x and y intercepts, make sure you understand the difference between your x's and y's. When we talk about x, we have a conversation right here. Where does this graph cross my x-axis? If I were to trace or color the graph, I can see where it crosses my x-axis. Every time that I have an x value and an output of 0, we have to remember a 0 or an x-intercept is my output of 0. The easiest way to find them is to go to the table and look for. Now our y-intercepts are still an interesting conversation because that's where our graph crosses the y-axis. So when we're looking at the y-axis, that's an input of 0, meaning 0 goes in, and I'm looking at what is the output when that input is 0. So when I go to my table of values, I can again have an x equal to 0. All right, the next conversation that we have with graphs is one that kids still find a little bit difficult. And this increasing and decreasing behavior references this graph here. Where my slope is positive, that's where I am increasing. So when I look here, each of these graphs, as I read from left to right, and I'm moving as my x's get bigger, so do my y's. When I use interval notation, I'm going to just talk about the sections, but I'm always going to use parentheses because I'm looking at where the graph is changing. At these points specifically, nothing has happened. It's the movement. And I want to make sure that I'm always talking about my x's. So from an x value of 5 to negative 2, my graph is growing. It's getting bigger. From a graph of x value of 1 to 3, my graph is again growing or getting bigger. When I'm talking about a decreasing interval, I'm talking about where is the slope negative? Where is my graph getting smaller? So when I look here at an interval of 3 to 5, I want you to picture a car driving. Where is it decreasing? From this x value to this x value. Remember, it's just a conversation about x's. Always our x values whenever we're talking about our increasing or decreasing behavior. Something this graph has here is a constant. And there's no change for this graph at this point. Remember, you're always reading from left to right, and remember, it's a conversation about our x values. As I'm going, what tick marks are going to talk to me about the behavior of that graph. All right, our last conversation has to do with end behavior, and I want to make sure that you know that this picture here goes with the words underneath. So if we want to, we can draw a line around this conversation and focus here. Our end behavior talks about what is happening at the end of my graph. If you'll notice, if my graph has an even exponent, my end behavior matches. So this is an x to the 4th graph, and this is an x squared graph. If it's either up, up, it's positive. If it's down, down, it's going to be negative. When I have an odd exponent, I can go ahead and recognize that my end behaviors are opposites. If I start low and end high, it's positive. If I start high and end low, it's going to be negative. So when we talk about the end behavior, I mean as x approaches negative infinity. That means as my x's get smaller and smaller and smaller, and you're asking yourself what happens to y, or your output values. As you go to the left, what is y doing? Here it's increasing, here it's decreasing, here it's decreasing, here it's increasing. Your answers for your end behavior, if you have functions or graphs with arrows on the end, are usually going to be either infinity in a positive direction, or it's going to be infinity in a negative direction. As x approaches positive infinity means you're moving to the right. As x gets bigger, what is y doing? And you're telling yourself the story of where is your graph going? What happens to y? Okay, so now we're going to start analyzing these graphs by looking at our new parent function, which is going to be the square root function. And if you get your graphing calculator, you can go ahead and go to your y is equal to, and you can enter in the square root of x. Looking at a graph of it shows you an interesting graph. Notice it's only in one of the quadrants. When I go to the table of values, I have 0, 0, but look what happens if I go into the negatives. And I want you to think about why I can't have a negative value. And look at this. Look how big my x's are getting, and my y's don't really seem to be growing much at all. So when we start talking about our parent function, our starting point is always going to be 0, 0. Because anything with a negative square root is going to be undefined. That I cannot take the square root of a negative number. So the interesting thing, for the first time, we don't have a domain function that continues on both sides of my y-axis. So my domain is going to include 0 and go to infinity. My range is going to include 0 and also go to infinity. This y-intercept is going to start at 0, 0, and my 0 is at 0, 0. Anytime I have 0, 0, my x and y intercepts match. My increasing interval for this one, when you look at it, your graph is always getting slightly bigger and bigger. So starting from 0 and going to infinity, my graph is increasing, and it is never decreasing. Is it a function? Yes, it passes the vertical line test. Is it one-to-one? Yes. Every square root is unique. When we have it being continuous, yes, it's continuous. When we talk about our extrema, we can have a minimum of 0, 0, and then for our maximum, there's going to be none. As x approaches positive infinity, so does y. So our tip for graphing is find our starting point and then choose 2 to 3 points to the right, where we're talking about where this graph can grow. So there's a lot more blanks here than we actually need. So I'm looking for values that I can graph. So the square root of 1 is 1. And my next perfect square doesn't hit until 4. My square root of 4 is 2. My next perfect square is 9, which is going to be 3. Now I can fill in this chart with my integers, and you'll notice a pattern. But when it comes to graphing, 0, 0, 1, 1, 4, 2, 9, 3 is going to be all that my graph shows. Notice it's a curve that will continue on. If you turn it sideways, it looks like half of a parabola, doesn't it? What we're going to talk about is how this is actually the inverse of my exponents. And we're going to talk about the relationship between finding the square root of something and squaring it. All right, let's talk about our cube root function. Now the cube root function is a little bit different. As a parent function, we can go ahead and do math, and then we could enter in cube root of x. And then, of course, look at the graph. Now what's interesting is our cube root does have this negative aspect. And if you think about it, can I take the cube root of a negative number? Absolutely. When I go to my table of values, I have no errors. I have no restrictions. I'm able to have positive and negative input and output values. And we understand that because we can take the cube root of a negative number. So our interesting part of graphing here is we're going to go ahead and we're going to put 0, 0 in the middle of our table of values, because unlike our square root, we're going to be able to have positive and negative values. Our center point is going to be 0, 0. Our domain if you look at the graph, notice we don't have any restrictions. We can talk about negative infinity to positive infinity, our range, negative infinity to positive infinity. Our y-intercept of our parent function is going to be 0, 0. Same with the zeros. When we talk about our increasing and decreasing interval, the graph is always going to be increasing as I move from left to right. It is never going to be decreasing. Is it a function? Yes. It passes the vertical line test. Is it one-to-one? Yes. Is it continuous? Yes. And extrema, we're going to go with none. As x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity. And here's our tip for graphing. It's going to be choose 2 points to the left and 2 points to the right. So when we go to our table of values, we're going to try to find values that are integers that are easy to graph. So 1, 1 and -1, -1 are both easy points. Now because it's my cube, you know the next point that comes out evenly is going to be a -8, which is -2. And of course the cube root of -27. That's obviously going to be off of our graph, but we can still go ahead and fill it in. Now, when you look at this, think about your perfect cubes as an input, because instead of taking something to the third power, I'm actually looking for the cube root. I'm taking the inverse of that operation. Alright, so when we go to graph these, I like 0, 0, 1, 1, and -1, -1. So it's hard to see on the calculator, but it's easy to see here where it crosses. And I'm sure about this 1-to-1 and continuous because I don't ever have a repeat in my output or in my input. So over 8 up 2, over -8 down 2, my 3 and my 27 are not going to meet. So when I have my graph, the interesting thing is if I turn it, that's going to be looking a lot like my cubic function, isn't it? But we can go ahead and say our cube root function has those properties similar to it. All right, let's go on and keep talking about, because next up is transformations.